What's up, nerds? Let's review radicals and factoring. So, as we start, let's go ahead and go over some vocabulary we're going to use. This symbol on the outside here is called a radical, and it's going to be really important that we call it a radical and not a square root symbol, which it is. But eventually, we're going to get to using a radical for roots other than square roots. We're going to do cube roots and quartic roots. So it's a good habit to just call it a radical in general. Okay, the thing that's inside the radical can be called the radicand, but more often than not, I'm going to call it an argument. And the reason I'm going to call it an argument is because radicands only apply to radicals. It's only used for whatever is inside the radical. However, argument is used for a lot of different functions. The inside of any function can be called an argument. So I know we don't know these yet, but we are going to learn something called a logarithm. And so when we do a logarithm, the x is inside that logarithm, and I would call x the argument of the log. Okay, similarly, you probably recognize sine, cosine, or tangent. And again, the x is inside the sine function, so I would call x the argument of this trig function. So since we use argument a whole lot more than we use the word radicand, that's why I'm going to stick with the word argument mostly. So let's review some properties real quick. The multiplication property says that if I am multiplying two things underneath a radical, I can actually split them up into two different radicals and take the square roots separately. They're still going to be equivalent expressions. Similarly, I can use the division property, and I can split up a fraction that's underneath a radical and just take the square root of the numerator separately than the square root of the denominator. And we'll see why that's handy in a little bit. But first, in this first example, what is so important for you to just embody in your soul is that these properties work for multiplication and division. They absolutely do not work for addition and subtraction. So let's look at why. Or really not why, but let's kind of verify that they in fact don't work. Okay, so looking at example A here. Hopefully you recognize that I could rewrite the square root of 4 as the square root of 3 plus 1. These two things on the right side are equivalent to each other because that 3 plus 1 is still underneath the square root. You could type either of those in your calculator and you're going to get that both of these equal 2. Square root of 4 equals 2. The square root of 3 plus 1, all underneath just one radical, does equal 2. But what happens when I try and split them up? So if you type in this left side into your calculator, the square root of 3 separate from plus the square root of 1, you end up with 2.732 blah, 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 right? An irrational number, which obviously is not equal exactly to 2. Okay, so we can see that this property is definitely false. It does not work with addition. Okay, I told you it works with multiplication, but let's verify. Hopefully, again, you can see I could rewrite 6 as 2 times 3, all underneath one radical. And if you type this right-hand side into your calculator, you get that both of them equal 2.449. Okay, and let's check the left-hand side then. Type that into your calculator, square root 2 times square root 3. Again, you get 2.449, and not just those first 3 digits. The whole irrational decimal is exactly the same for both of these. So this property is absolutely true. Which I hope it is, because I told you it was true in the property of radicals. Okay, so again, just committing it to memory and in your soul and in your heart, you just know you can't do this. Okay, let's verify that even though I could rewrite 9 as 11 minus 2, both of these right-hand equations definitely equal 3. Okay, but if I try the left-hand side of that equation, we get 1.902, another irrational number that is not equal to 3. So we cannot split that up. False, false, false. Every time it's false. Please, please, please don't ever do this. But what we can do is D, because we have the division property. Let's verify that it works. 16 is the same as 48 divided by 3, which means I could write this as 48 divided by 3, all underneath one big radical there. And I can type any single one of these expressions into my calculator, and we're going to get 4 equals 4 equals 4. So this property is true for radicals. We can split up division and multiplication. We cannot split up addition and subtraction. Okay, and so for this chapter, it's going to be really important that you are familiar with your perfect squares. So I went ahead and listed your perfect squares from 1 to 20. And it's okay if you don't have all of these memorized, but what you do need to do is make yourself familiar enough that you recognize it's a special number. You should just be able to, like I said earlier, feel it in your soul. You should be able to look at, 225. And maybe you don't remember that it's 15 squared, but you should practice with these enough to just know, hey, that's a special number. I should know something about that. Should just give you a tingly feeling. Okay, so make yourself familiar with those. Let's move on to example 2. So given that some number squared is 4, what are the two possible values of x? Okay, well, hopefully you know that I could square 2. 2 times 2 is 4, but also negative 2 times negative 2 is 4, right? So 2 squared equals 4. Negative 2 squared also equals 4. So it looks like my solutions could be positive or negative 2. So how would I show the work for that, right? Because I went ahead and I do have now my two possible solutions. But we're going to be solving a lot with square roots and quadratics, which is why we're looking at this. So the way that I would show the show the work for this, I'd copy down the original problem, right? X squared equals 4. And we need to make sure that we end up with two solutions. So I need to remember that whenever I take the square root of both sides, the square root and squaring something are inverse operations. Just like adding and subtracting 2 are inverse operations. It makes the value go away. Okay, I need to remember to add this plus or minus sign there because there are two possible answers when I square something for the result to be positive. Okay, so when I take the plus or minus square root of both sides, we end up with x equals, and we have this positive or negative now, positive or negative 2. Okay, this is different from a problem in example 3, which already starts with a square root. So notice it just says x equals the square root of 4. The only value of x here is positive 2. And let's talk about why. So if I simplify this, x equals 2. Okay, one kind of lazy justification for this is try typing that in your calculator. If you type in square root of 4 in your calculator, it does not tell you the answer is positive and negative 2. It tells you that there's only one answer. The answer is 2. And the reason is that there was no plus or minus sign in the problem to begin with, okay? In example 2, we had to add the plus or minus sign because I know that when I square something, squaring a positive number can be positive, and squaring a negative number can also be positive. I am the one that introduced the square root. So that's why I also had to put that plus or minus. Okay, in example 3, the square root is printed there. So it only indicates the positive solution. If it wanted a plus or minus, the plus or minus would have had to be printed there. Okay, and that's part of a bigger conversation. So this note down below says all numbers do technically have two square roots. There is a positive and a negative root of a number. However, when we are using the radical symbol, because it's a function, right? It's the square root function. Functions can only produce one result. So the radical symbol only means the positive square root. And if you also want the negative square root, you need to use a negative sign with it. That's the whole point of the plus or minus. Okay, so that's going to be really important. I know it's a little uncomfortable at first to distinguish the difference, but we're going to have to practice enough to get used to that. So let's go ahead and start practicing and looking at the difference between examples A through D. Okay, so I need something times itself, or something squared, to equal 289. Okay, so if I take the positive or negative square root of both sides, so positive or negative square root of, and I'm being a little bit lazy, I'm just making one giant square root. Might not be best form, but you can see whatever I do to one side, I do to the other. I'm taking the positive or negative square root of both. Okay, and we end up with the square root of something squared is just x equals the square root of 289. That's one of those square numbers that we have listed up above. It is positive or negative 17. Okay, again, because I could plug in positive 17 and 17 squared is 289, negative 17 squared, also positive 289, right? So I know that that is both solutions. Versus example B, where the square root is already printed there. There is no plus or minus sign. And I'm not the one adding that square root. It's not saying that x squared equals 36. It's just asking me, what's the square root of 36? And that's something you could type in your calculator and verify that it is only the positive square root. We just have one solution when it is written like this. Okay, C, we are the ones that are taking the square root here. So plus or minus square root of both sides, and we end up with positive or negative 7. So I have two solutions. Versus D again, that square root is already printed there, so all I have to do is simplify. The square root of 225 is 15. Alrighty. So, simplifying radicals, we need to use that multiplication property in order to break up radicals into a perfect square factor and what I consider to be just the leftovers, whatever I cannot simplify anymore because it's an irrational number. And this is really important for us to do because we like to deal with numbers that are as small as possible and simplified, and we don't want to have to write irrational numbers as long, trashy decimals, right? We just want to keep them as small and concise and as easy to write as possible. So let's look at the most efficient way to do this. In example A here, we can break up the square root of 18 into, I know that 18 is 9 times 2, and the multiplication property of radicals says I can split this up into two separate radicals, and it's still going to equal the square root of 18. You can check every step of your work by typing it in the calculator, and it should always equal the same irrational number. Okay? And now I can simplify the square root of 9. The square root of 9 is 3. Square root of 2 is irrational, but it's as small as it can possibly get. And I have simplified the square root of 18 now. Okay? b has a coefficient in front, but it's not going to change anything about what we do. We still just copy down the problem. 5 stays in front. It's being multiplied by the square root. And it's going to take some practice, but you need to go through and see what is the biggest perfect square that goes into 240. Because I could do 4 times 60. The issue, though, is that 60 is still divisible by a perfect square. 60 is 4 times 15. And so you can take a couple steps to simplify, especially if you're not super familiar with your perfect squares. But I want to try and do this in as few steps as possible. Okay, so instead of picking 4 and 60, I'm going to go ahead and choose 16 and 15. Because 16 is the biggest perfect square that's going to go into 240. Okay, so then again, I can go ahead and split apart that radical. I can go ahead and simplify. And remember, if there is no symbol in between two numbers, like between the 5 and the square root of 16, the implication is that I am multiplying those. So when I simplify the square root of 16, I'm going to multiply that times 5, and I am also multiplying that times the square root of 15. We just don't really have to write this little square, or I'm sorry, this little multiplication in the middle, since we have a symbol, a different symbol in between there. Okay, so then 5 times 4 is 20, root 15, and that is equivalent to 5 times the square root of 40, or 240. It is just simplified. Okay, for C, we can just use that division property real quick, where we know that we can take the square root of the numerator and the square root of the denominator separately, and we end up with 2 over 3. Pretty straightforward. Okay, D. There's 2 different roots you could do with D. I'm just going to go ahead and leave this fraction as it is. You could simplify it first, but weirdly that's actually going to make your job here harder. So I'm going to go ahead and rewrite that. Okay, I know I can take the square root of 81, right? My denominator is just going to be 9. Okay, but my numerator, I need to look at square root of 45 and ask myself, can I divide 45 by a perfect square? And in fact, I can. I can split 45 up into the square root of 9 times the square root of 5, right? Because 9 times 5 is 45. 9 is a perfect square. Okay, let's talk about a common mistake. We cannot simplify the 9s at this point because this is a normal 9 and this is a 9 that is underneath the square root. We would have to simplify the square root first before I could cancel it out. They both have to be what I just called a normal number. Okay, so let's go ahead and simplify first. Square root of 9 is 3. Square root 5. Goodness, the birds are really going at it, huh? Okay, and now that 3 is outside of the radical, right? It is just a normal number. I can actually simplify these. 9 divided by 3 is there's going to be just 3 left over in the denominator there. My final answer is square root of 5 over 3. Okay, and C and D kind of open up a bigger conversation about what happens when the denominator is not a perfect square, and why do we have to take these extra steps if the denominator is not a perfect square? So it's just considered to be math etiquette to not leave radicals in the denominator of a fraction. There's a lot of things we do to standardize answers, and part of the reason we do that is partially to just make it easier for us to compare our answers and check them. It would be really annoying if every single one of us got a different answer, but we're all right, They're just not all in the same form. So part of the reason for these math etiquette things is just to make sure that when we are comparing things, that it's obvious that things are the same or they're different. So one of the things we do in order to do that is we don't leave radicals in the denominator. So we call the process of getting the radical out of the denominator rationalizing the denominator. And our steps to rationalize are going to be to simplify the fraction if possible. And then we're going to multiply by a creative version of 1. Because multiplying something by 1 does not change the value of it, right? We know multiplying by 1, that's an identity property. I can multiply by 1, but we're going to be creative with our version of 1. So let's go ahead and jump into example A so you can see what I mean when I say that. So in example A, there's nothing to simplify from the beginning here, okay? But my goal is to be able to rewrite this so that the denominator does not have a square root anymore or a radical anymore. Okay, so my creative version of 1 is going to be a number that when I multiply it in the denominator, it's gonna make that 7 into a perfect square. So if I multiply by the square root of 7 over the square root of 7, okay, this is just a big old giant creative version of 1, right? And multiplying by 1 doesn't change the value, but my creative version of 1 is going to change the way it looks. We end up with the square root of 35 over the square root of 49, which the square root of 49 is just 7. I cannot simplify the square root of 35. There's no perfect square factors there. So I am done. I have successfully rationalized the denominator. Okay, and again, we mentioned this earlier, but remember we cannot simplify this, right? I know that 7 does go into 35 an even number of times, or in fact, an odd number of times. But since that 35 is underneath the square root, we cannot simplify this anymore. That is as simple as this problem gets. And you can verify that in your calculator, right? If you thought that they canceled out and you're like, oh, this just equals the square root of 5. Right, because 35 divided by 7. If you type those two in your calculator, they are in fact not the same thing. Okay, so let's try that again. Here we go in B, and we can actually, I noticed that both of those are even at least, so I definitely can simplify that fraction. So I'm going to go ahead and simplify this. We can actually divide them both by 4, I believe. We're going to end up with the square root of 50 over the square root of 7. Oh, and look at that. We get to use the same creative version of 1 again, because my goal is to get the radical out of the denominator. So when I'm thinking of my creative version of 1, I'm thinking, what can I multiply that denominator by? And in order for it to equal 1, I need to multiply the numerator by the same thing. This is just a big old giant creative version of 1. And now we end up with the square root of 350 over the square root of 49. Which I can simplify both of those, right? So I know 25 goes into the square root of 350, and it is 25 times 14. Okay, and then I can go ahead and simplify that square root of 25. 5 square root of 14 over 7. And we are rationalized, or I suppose our denominator is rationalized at this point. Alrighty, so maybe try C and D on your own, see if you can come up with them, and you can check back in with me on C. That 2 is not going to affect anything, right? I'm just going to copy it down. It's really important that you are not lazy and copying things down, because that's how you just make really silly, avoidable mistakes. Okay, my creative version of 1, I choose based on the denominator. Has to be the same on top and bottom for it to be a giant creative version of 1. Okay, another thing I'm going to do is I'm going to go ahead and put that coefficient 2 up in the numerator. Okay, so I'm going to end up with 2 square root of 10 over the square root of 4, which, ooh, this looks like it's going to get real exciting because square root of 4 is just 2. The 2's are going to cancel because they're both just normal numbers. Does not cancel with the 10 inside because that is underneath a square root. We can think of the square root almost as like protecting that number that's underneath. It does not want to mingle with any of my other numbers. And there we go. That's a whole lot prettier number than the problem we started out with. So nice and simplified there. Okay, D, I'm going to show you something that you have the option of doing. You do not have to do this. You're just going to have more simplifying to do at the end. So if you solved it already a different way, great. Compare it to how I'm going to solve and see if it's different. Okay, I can look at this and I recognize, okay, 169 is already a perfect square, and 8 is pretty easy to break up into something that is a perfect square and my rational number that's left over. Okay, so let's go ahead and rewrite that as, I already know the square root of 169 is 13 over, okay, and I'm going to break 8 up into the square root of 4 times the square root of 2. Okay, and this is going to make it so much smaller for my creative version of 1 than if I had tried to simplify at the end, which maybe you did, which is not a bad thing. Hopefully you got to the same place I will. So 13 over 2 square root 2. And now I can do my creative version of 1. And we end up with 13 times the square root of 2 over 2 times the square root of 4, right? I just combine what's under the radicals there. The square root of 4 is 2. So I end up with 13 times the square root of 2 over 2 times 2, right? There was no operation in the middle there, so we assume it to be multiplication. And that is going to simplify to 13 square root of 2 over 4. Look at that. Alrighty. Okay, so that's our review of simplifying radicals, which is a whole lot longer than our review of factoring, because we're just going to start with very basic factoring to review. So, it's really important that you get super comfortable with factoring because hopefully this is no surprise. It is going to get more complicated later in this course and in future courses, and it is so important. So if we think of factoring as reverse distribution, hopefully it's going to make that factoring a whole lot easier. So for example 6, I just want us to practice foiling out or distributing a couple problems to really get that process solid in our head. So x times x is going to be x squared. X times 3 is going to be 3x. 4 times x is going to be plus 4x. And 4 times 3 is going to be 12. Okay? And then notice, this is going to be really important, that I combine these two middle terms together because they are like terms, and we end up with x squared plus 7x plus 12. Okay, let's do a couple more. Maybe pause the video here because this you should be pretty comfortable with already, but I do want you to make sure that you are writing out every single step like I am. That is going to be so helpful in training your brain to factor quickly and efficiently. Okay, notice we are combining these two middle terms. big old truck driving by. Okay, and again, notice I'm writing out every single step. It is so good for your brain to see what's happening. I know you are perfectly capable of doing a lot of things in your head, but sometimes hiding steps is just making things harder on yourself, and it's going to make harder problems more difficult. Whereas if you're used to showing your work, I promise it really does make your life easier in the long run. Ooh, this one's interesting, because it sure looks like these two terms are going to go away. They're going to disappear there. All right. Oh, I forgot to box that answer in. Okay, so there's my distribution. And every single one, I ended up with two like terms that I combined. And that came from the inner multiplication and that outer multiplication in the foiling acronym. Okay, so when I am factoring, I know you guys have learned a lot of different strategies for factoring, but I highly encourage you, try to do as much as you can. I know I just said show all your work, but try to do as much as you can in your head by seeing that foiling process in your head. Okay, so let's look at this first example, and I'm going to make sure to leave the example above on the screen. Okay, example A looks a whole lot like the style of answer I have in A of example 6. Okay, so I know when I factor this, I'm going to end up with 2 parentheses. And I know that this first term here comes from multiplying just these first 2 terms. It never combined with anything else. Okay, so the only way to get this x squared is by multiplying these 2 things together. So that's what tells me automatically I know this has to be an x and an x. Okay, so another easy thing to look at is this last term, this last term. Okay, it also did not combine with anything else. It came from this part of the foiling, right? So I know that this negative 16 has to come from multiplying 2 things here. And the question is, what do I put there? Because, I mean, there's a lot of different ways to get negative 16. Negative 1 times positive 16 equals negative 16. Okay, but that's not going to give me the right middle number, right? That middle number came from multiplying these 2 numbers together and these 2 numbers together. Right, so that's how I get the x there. I need to multiply these 2 together and these 2 together, and they need to combine to be negative 6. Okay, well now they combine to be positive 15. So I know that that's definitely not right. Okay, so let me go ahead and erase those. So it's not 1 and 16. Okay, let's just kind of go through and brainstorm other things. Okay, well if it's not 1 and 16, maybe 2 and 8. So if I do minus 2 and positive 8, okay, so thinking about that, negative 2 times 8 is negative 16. Cool, cool, cool. Okay, and negative 2 plus 8 is positive 6. Okay, so I'm so close, I just have the wrong signs. So I just need to say, okay, well, I could also get negative 16 by doing plus 2 and minus 8, okay? And 2 times negative 8 is negative 16, good, good, good. And 2, oh, I'm sorry, so 2x and negative 8x is negative 6x. So I know that this would FOIL out to be the correct answer. Okay, so I know that the factoring of this is x plus 2 times x minus 8. Okay, and I know that this process might be uncomfortable at first, but it truly is the most efficient way to factor, and it is gonna make your brain so much stronger to struggle with this a little bit at first, but I promise you'll get the hang of it, and it's gonna make your life so much better moving forward. Okay, so let's try that with B. So with B, I'm gonna start with my 2 parentheses. Okay, I know that this has to come from these first 2 terms here. So this is gonna be the only way to break that up, it's gotta be a 2x and a 1x. And you could put the 2x second, nothing said it had to go first. Okay, we need to be a little bit careful on this one because, okay, this negative 45 has to come from these 2 being multiplied. Okay, but remember when I continue foiling this out, that this 2 is gonna get multiplied by whatever this factor is. And then these 2 need to combine. Okay, so some side work that I can do to help me, which may be helpful for you to do at first, is to multiply these 2. It's called the AC method. So because I know that the 2 is gonna multiply with whatever's over here, I'm gonna try and find factors of negative 90 that are going to combine to be 27. So I'm not gonna worry about the negative for now. I just know that I'm gonna be subtracting these values, but 1 times 90 definitely doesn't combine to 27. 2 times 45 does not. 3 times 30, oh, it looks like I have my winner, right? Because 3 minus 30 is going to be 37. Nope, it's gonna be 27 when I subtract. Okay, so then I need to make sure that these 2 rainbows, so this guy and this guy, need to end up multiplying to 3 and 30 somehow. Okay, so I can see that hopefully by 2 times 15 is gonna be 30, and 3, there we go, so now I have 3 and 30 on my 2 green arcs there. And I can verify that 3 times 15 is 45. So I have all the right factors here, I just gotta get the right signs. And in order for those to combine to be a positive 27, it has to be positive 30 minus 3. And I have factored this now. 2x minus 3 times x plus 15. Alrighty. So this one's a little more challenging to be sure, but let's start the same way. Let's work on making our brain stronger. And maybe let's just write down 2 different options here. Because what's challenging is there's 2 different ways that I could break up this 4x squared in this first spot here. It could be 4x times 1x, or it could be 2x times 2x. And I'm just not sure which one's gonna work yet. So let's go ahead and leave it for now and look at this last value. Okay, so factors of 3, fortunately, are not all that long. But remember when I'm asking what adds up to 4 in the middle here, right? What adds up to this number? We need to do that AC method. We need to multiply those and things. What factors of negative 12 are gonna combine to be 4? So I have 1 and 12, that doesn't work. 2 and 6 looks like the money, right? Because 6 minus 2 is 4, or in fact, really we want 2 minus 6 is negative 4. Okay, so 2 and 6. There's absolutely no way I could fill this in because this 4 is going to multiply by that number. 4 times nothing is going to give me either 2 or 6. So I think this parentheses might be a bad option. Okay, 2 and 6. So these two are going to multiply and these two are going to multiply. So 1 times 3, right? Because 2 times 1 is 2 and 2 times 3 is 6. So that's looking pretty good. And I can double check and see that 3 times 1 is 3. Okay, and then I wanted that to be negative 4, so the 6 has to be negative, right? So negative 3 times 2 is negative 6, 2 times positive 1, and there we go. 2x minus 3 and 2x plus 1. Last one. Ooh, this is just like example D above, where there is no term in the middle. So this is a really special style of quadratic that we call a difference of squares, where there is no single x term in the middle. And I am subtracting two numbers that are perfect squares. So if we compare that to example D above, notice that in example D, we have almost the same exact parentheses, and that's how this middle term ends up going away. The only difference is that one has a positive and one has a negative. And again, that's how those middle two terms negate each other. Okay, and that's only going to work if I have perfect squares. So I can jump straight to my answer. I already know that this to factor, and for that middle term to go away, 2x times 2x is 4x squared. 7 times 7 is 49. I need to have one positive and one negative for it to be negative 49. And I know that that would make that minus 14x and plus 14x when I FOIL cancel out. So there is my final answer. So there's our nice little review. Happy practicing, and I will see you in the next video.